Today I'm going to introduce our work on Bayesian MRI reconstruction with structured uncertainty distributions, which is joint work with Ivor Simpson and Neill Campbell. Our motivations for this work are outlined here. I will go through them in detail due to time constraints. However, our approach is to define tractable distributions on image space and combine them with generative priors using variational inference, and this gives us the robustness of optimization-based approaches, but also the capabilities of generative and probabilistic-based approaches. And the main benefits that we get from this are outlined in the bullet points at the bottom here. So what are these distributions? We call them structured uncertainty distributions, and these are sparse Gaussian distributions defined on image space. More specifically, we represent images as Gaussian Markov random fields, and in a Gaussian Markov random field, you represent your image as a graph, where connected components in the graph represent pixels that are directly correlated to one another, in the sense that if you condition on all other pixels in the image, then the conditional correlation between these two pixels is still non-zero. And this non-zero conditional correlation corresponds to a non-zero entry in the precision matrix of the corresponding Gaussian distribution. Precision matrix, the inverse of the covariance matrix. We can capture very fine details between pixels by representing them this way, and the corresponding covariance, if you invert this precision matrix, captures longer scale correlations through the Markovian structure of the graph that is defined. And so using this distribution, we can see an example here of the sorts of information that is captured. On the left-hand side, we have the ground truth image. So this is the real and complex channels. The second column shows the mean of the VAE decoder. So in a VAE, you decode a latent variable into a Gaussian distribution. This is the mean of that Gaussian distribution. You can see that it captures the large-scale structure, but none of the fine details. And this is very common of VAE reconstructions. However, in the third column, we can see the types of fine-grained details that our covariance is able to capture. And so what we've done here is we've sampled from the VAE decoder and we've subtracted the mean, and what's left over is the residual structure. And this residual structure, you can see, contains realistic bone textures and some finer structures, which were not able to be resolved by the mean of the VAE decoder. And now this final column tells us a little bit about the interpixel correlations that exist. So this is a heat map of how correlated each pixel is to the pixel defined by this little white star here. And so all of these red pixels are positively correlated, all of the blue pixels are negatively correlated. Okay, so we want to do inference with these distributions, and so we need a model to link our unknown variables to our observations. I won't go through all the details here because of time constraints. However, the key point is that the VAE structure that we use as a prior induces a Bayesian hierarchical model where we need to jointly estimate posteriors over the latent Z and the unknown image X. We define variational approximations to the posterior over Z as a multivariate normal distribution and over X as a structured uncertainty distribution. Because our posterior approximation is a Gaussian distribution, we can read off our approximated posterior statistics, for example, the mean, the covariance, the pixelwise standard deviations, and therefore credible intervals. And we can also produce the sorts of visualizations that we showed for the VAE. However, in rows 2 to 4, we are showing the corresponding visualizations for posteriors after conditioning on 2.5% of k-space data up to 10% of k-space data. So for the most severely undersampled case, you can see that the posterior residual here shows very strong evidence of the prior that was used within its structure. And this is indicative of the fact that 2.5% of k-space isn't very much. You can't resolve things to a very high resolution. In fact, the naive reconstruction is completely blurry. And so in order to fill in the gaps here, the prior distribution is influencing what this reconstruction looks like quite heavily. A similar story is told with the pixelwise correlation. So this is how correlated each pixel is to this red starred pixel here in the top row. And these spread out quite far, which is indicative of the fact that the data is not sufficient to overwhelm the interpixel correlations that exist in the posterior. At 5%, the structure breaks down somewhat, but is still quite visible, and these correlation ranges reduce. At 10%, it breaks down some more, and the correlation reduces even further. And in the paper, we got to 40% and showed that the correlation breaks down completely. So if we compare our method to diffusion posterior sampling, which is a very popular method for solving inverse problems with generative models at the moment, we see that our method has higher PSNRs across the board for both very low and higher data quantities. And also for the severely undersampled setting, that our method tends to produce realistic fine structures, whereas the diffusion posterior sampler often produces hallucinations which are unrealistic or anatomically incorrect. So in conclusion, structured uncertainty distribution-based reconstruction provides tractable posterior approximations such that you can read off your posterior statistics, visually interpretable posterior information beyond pixelwise variance, and so interpixel correlations and such, and competitive reconstruction accuracy, if not superior, when compared with modern generative approaches.